Sorry for that. Okay, so my name is Sharon Lapiner. I work with Avishai, and I'm going to talk about the blue nuggets and the transition of the as a critical transition of many properties of the galaxy. And I'm going to focus mainly on the post-compaction rings that we see, but I'm using the Vela simulations by Daniel Cedzino. Avishai already showed this. This is just the sequence of events where you see the wet compaction, blue nugget. This is the post-blue nugget where you start to see VDI disk and the ring. And this is a post-compaction ring which occurs later in time. So Avishai showed for one galaxy. Here I'm showing for a large subsample of high-mass galaxies the compaction event. It's all stacked on the time of compaction, which is the A blue nugget is the time of compaction. I'm stacking everything. So if you look only on the solid lines, you'll see this is the compaction event where there's a steep rise, followed by depletion of the gas. And the same thing, this is for the star formation rate. And if I look at the same curves, but with the stellar mass, I can see qualitatively the same shape, the same behavior. So I can see here again the compaction, this is the peak of compaction, and depletion of gas, which gives me this critical mass, which is around 9.5 or, sorry, 10. So again, this is the critical mass. And so the rings, this is the observed H-alpha rings. This is by Genzel 2014. And showing here the surface density of H-alpha. And this is in simulations. You see a ring post-compaction. It's a clumpy ring with a passive core. There's very little gas there. And zooming out, okay. Zooming out, we see this is gas that's coming in from the streams, which is fresh gas. It has also low metallicity, which I did already check. And to see the evolution in the profiles, this is from the Kela 2016. If we look at this purple line is before compaction, before the blue nugget. The blue line is during the blue nugget, and the green line is after. When it's between the compaction and the red nugget. So if we look at the evolution, we'll see a cusp is created in the gas and star formation rate. And from the blue nugget to the red nugget, you see the gas is depleted from the center. The star formation rate is decreased. You see all the curves of the stellar mass are self-similar. The growth is the same. And in the star formation rate, you see that the inner part is has low specific star formation rate. And there's a ring forming here when there's gas depletion at the time of the red nugget. So we look at kinematics, we find that if we look at, okay, so this line is V phi, and this one is sigma r. So V over sigma, pre-compaction is 1 or less, which means it's perturbed gas, it's not really a disk. And post-compaction, it's rotating disk. In the stars, we can see, sorry, in the stars, we can see that there's a rise in V phi, but these stars are dominated by the bulge. So if we look only at the disk stars, we'll see something similar to the gas. So we see a transition from sigma, V over sigma of 1 to V over sigma over 2 and more than that. This is the spin of the galaxy. This is the spin of the gas in the galaxy and the spin of the stars in the galaxy. And this is again stacked on the compaction event. So we see a low spin before compaction and high spin after compaction. So this is basically the extended ring you've seen before. And if you look at this branch, which is going down again, these are the low mass galaxies which tend to go through another later compaction event. And the triggers of compaction, so we find roughly 50% of merger-driven compactions and about 30 that are something else. They can be VDI, counter-rotating streams. They're not, we don't find any mergers to associate with it. So the compaction is a dramatic transition. We see this in many, many other properties, which I won't have time to show. It marks the transition of many properties and occurs at a typical stellar mass, also virial mass, or virial velocity, which is very tight around the blue nugget phase. So the blue nugget triggers an inside-out quenching, where you see the quenching at the center, right after compaction. And post-blue nugget, you get an extended disk, where you see star formation rate at the disk, and could also, the stellar part of the disk is built up by this gas stream, and also by dry merger. Okay. It's an over. Thank you.
Any question for Sharon? No. I have a question regarding the when you showed at the beginning, the stack profiles of compaction. Refer to the time of compaction or stellar mass. Yes.
Oh, I shouldn't have done that.
No, it's just, it looks to me that when you plot it against the compaction, the time of compaction, the time of compaction is exactly the time when the galaxy starts to be baryon dominated.
It's a bit before that.
Okay, but this is kind of almost at the same. While when you plot it against stellar mass, it's like very decoupled. So you start to be baryon dominated well before the critical mass. Is there an explanation for that, or?
Well, the fact. So we see the onset of compaction usually slightly before this transition from dark matter dominated to baryon dominated. So it's usually we see this during compaction, during the event of compaction, the stellar part is created in the center, and then it's becoming baryon. So it's usually either very close or slightly before compaction.
Can you plot the other one, in which you plotted with stellar mass?
Yeah.
Yeah, this is what I'm referring to. So you see it's one dex before. So you say that the okay, because at the moment
this is about the time of the baryon dominated. It's slightly before that if you include also the gas.
Okay.
But it's usually around
9 a bit before. Any other question? Near?
Oh, yeah. So O is around the onset of compaction. A few snapshots before the onset. OB is between the onset and the compaction itself. They seem to be about the same.
I think David had a question.
small masses. But I notice the alcohol already, of course, Isaiah looking at the masses to see if they full masses.
Well, yes, because I'm looking at the major compaction event. So there could be other small compaction events before or after, but this one is the one that makes the real difference in the evolution of the galaxy. This one is the one I find that creates a very high stellar mass, very sharply. So there are other compaction events, yes.
Any last question? Okay, here again.
Is it still the case that you find in the simulations that you never really form this prior to the connection, that all the big state, big prominent distance simulations occur in the post-connection state?
Almost, because in some very massive galaxies, you can see a very early compaction event that did create a small disk, but was perturbed and was gone with a big compaction event. So it's almost, in most cases, the disk is formed after the major compaction event. Well, I'm not sure yet.
So that just the shape of the central potential prevents formation.
Okay, I think we should move on. Let's thank Sharon again.